Thank you very much, Mark. Welcome, everyone. Thank you so much for joining us today for the Grasp on Robotics series. As a quick reminder, this and previously recorded talks can be found on our YouTube channel and website. Also, throughout the talk, please submit your questions using the button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. Now, I would like to introduce our Grasp faculty host for today's talk, Dr. Pratik Chauhari, Assistant Professor at the Electrical and Systems Engineering Department within the School of Engineering here at the University of Pennsylvania. Thank you very much.
Thank you, Gabby. Thank you, Mark, for a nice introduction to all the things going on within GRASP also. I'm very glad to introduce Professor Byron Boots. Byron is an associate professor in the Paul Allen Computer Science Engineering Department at the University of Washington. He received his PhD from the Machine Learning Department at Carnegie Mellon University, where he worked with Jeff Gordon. And if you see Byron's work, and I'm sure many of us are quite familiar with a lot of his papers, it shows a very strong mix of learning-based methods where he has made fundamental contributions to machine learning, artificial intelligence, but also very deep contributions to control robotics. A lot of this work has been quite influential both in practice and in academia broadly. Some of the most fascinating demonstrations or the most fascinating papers that have come out of his group that I personally have had an enormous time enjoying and reading include stuff on localization and mapping, rally racing, which I think he might talk about it a little bit in his talk, robot manipulation these days that he's doing at Washington. And you see impact in both these communities from Byron. So he has had, I think, a very unique tradition of winning best paper awards in very broad range of conferences. So take it, be it ICML and AI stats kind of things, or also RSS, IGRR, JMLR, these robotics places. Byron was the recipient of the RSS Early Career Award recently. He has been a recipient of the NSF Career Award a couple of years ago. He was awarded the Outstanding Junior Faculty at Georgia Tech, where he was until recently. Very glad to have Byron here, excited to see what he talks about, and I will let him take it from here.
All right, thank you for the wonderful introduction. Let me share my screen and get set up. Okay. Oops, 1 second. All right, so today what I want to do is I want to share some of my own perspectives on machine learning for adaptive robotic systems. And the purpose of this talk is basically to try to think about how machine learning and controls and how these areas should maybe interact with each other and how we can deploy them on robotic systems effectively. So this is basically a set of personal perspectives where I'm going to be sharing some, I think, interesting ideas and food for thought. I'll be deriving some stuff that you may be familiar with, things like model predictive control from a different perspective. So some of the stuff might be quite strange to folks who are more controls oriented. But I think there's some pretty interesting things we can do when you start to sort of step back and think about how different areas interact. So I want to just start by thinking very generally about machine learning for robotics. And this is a really big area. It includes many different tools, including reinforcement learning, learning from demonstration, online learning, ideas like sim to real, where you're basically training a policy or trying to figure out how to get a robot to work in simulation and then deploying it on a real robot, and ideas from controls like system identification and model predictive control. And these tools are often used in isolation or sometimes cobbled together in fairly ad hoc ways in order to try to get robots to achieve some complex task. So as someone who's interested in machine learning for robots, there are some natural questions which come up when you kind of think about all of these different tools. So what tools do we use for a specific task? How do these ideas fit together and interact with each other? And how do we build learning systems for more complex robotics tasks? So to get a handle on some of these questions, I want to provide some context for how I tend to think about robot learning. So first, I'm a big fan of these so-called no free lunch theorems, and I'm going to sort of use this idea in a sort of hand-wavy way. But the general idea behind no free lunch theorems is that machine learning works because of structure. And this is always true. And I think this is a very general and uncontroversial statement. Algorithms which work well in practice have structure, and it's structure in the function or policy class, in the objective function that you're trying to optimize, in the training or testing data sets, or in the learning algorithm itself, so in the optimization. And often there's a lot of structure. And so, like, if I think about computer vision or NLP, and recent advances in deep learning, these are not totally general, fully connected, multi-layer perceptrons, right? Like, we're using very structured policy or very structured function classes, structured data sets, and so on. So I think this is good news for robot learning. Robots and the tasks that we consider as roboticists have lots of structure in them. And the main question is, how do we make choices for our machine learning algorithms that can exploit this structure? All right, so in my talk today, I'm going to discuss several different areas and how they're connected while paying special attention to structure of learning problems. I'm going to start by discussing online learning and why it's, in my opinion, the right way to think about a wide range of robotics problems. And then I'll briefly discuss simulation and basically just emphasize that simulation is not reality. Just because you optimize something in a simulator, this is just not the same thing as running something on a real robot. And I think reinforcement learning folks are sometimes sloppy about this. So I'm just going to have kind of a brief digression about this. And then we'll get to sort of the heart of what I'm going to talk about today. So I'm going to discuss how these ideas of online learning and thinking about simulation as sort of a useful tool which can help us can be used to sort of derive model predictive control algorithms. So there's this non-standard perspective that I'm going to present that I think is actually quite useful and allows us to come up with new approaches to problems. I'll also show how the algorithms that we derive here can be used for some cool robotics tasks. And then finally, if there's time, I'll discuss some extensions to this work that sort of naturally fall out of this sort of newish perspective on model predictive control. I'll just sketch a few things there. Some of the work is in submission, so I don't want to go into too much details, but you can kind of see how the perspective that we build up might be useful for solving more complex robotics tasks. Okay, so let's get started by just sort of thinking about robotics and online learning. So what we'll do is we'll start to think about robotics learning problems in the abstract, and then we'll kind of get to more specific cases as the talk progresses. But we'll start with assuming that we have a robot, right? And that this robot can perceive the environment and take actions that change its relation to the environment. So it's receiving information, S corresponds to state, and A is an action. And this is the basic robotics paradigm. So this is what we teach our undergrads in the first course in robotics here at University of Washington. But this is a gross oversimplification of most robotics problems, right? So the type of robotics that I'm really interested in are robots which adapt their behavior with experience. And if we want to think about robots this way, we need to break the robot down a little bit further. So usually we assume that there's a policy. So this is a function that takes our states or observations as input and produces actions as output. And the policy itself has parameters, which are indicated by theta here. And if the parameters stay the same, then the robot's behavior stays the same. But if we want robots which can actually learn from their mistakes and handle more complex environments, then we might want to specify a learner which updates the parameters of the policy to improve at some task with experience. And so the idea is that when I come back to the same state, maybe I actually choose a different action in order to perform better at some task. And the learner is updating the parameters of the policy so that the policy is improving. So this is one way of thinking about an adaptive robotic system where we've really highlighted the robot's relationship to the environment. But this is not the only way of kind of breaking down this overall system. So we can alternatively focus on the learner and how it interacts with the system. So this is kind of a machine learning point of view rather than a robotics point of view. So here the learner is something which is interacting with this complex system, which consists of the policy and the robot in its environment. And so the way that this generally works is that the learner has access to an objective function for the task that we're trying to solve. And the objective receives feedback from the system. So it's receiving states and actions which are induced by running the policy with parameters theta. And this basically tells us how good the policy is, and in turn guides the learner, and this process sort of repeats. So for example, in like a reinforcement learning problem, we're often dealing with an objective which looks something like this, where we have some state action dependent cost that we're trying to minimize. And this is saying that we're essentially attempting to minimize the expected state action cost induced by the policy parameterized by theta, right? So the learner generates theta, we run the policy in the system. This generates a whole bunch of states and actions, which are then plugged into this cost function, which then kind of tells us how good theta is. Okay. So to make things cleaner, we'll just compress the policy's interaction with the environment down into this box, which I'm just calling system. Now, one way of thinking about the learning problem is through the lens of a type of machine learning algorithm called an online learning algorithm. And so in online learning, it proceeds by rounds. So at every round, this could be, for example, a time step in the system or an episode before resetting the system. The learner will choose parameters theta and execute a policy with those parameters in the system. We then next observe what actually happens. So what are the states and actions which are induced? And in the context of online learning, we're going to think about the system, right, as this adversary. It's going to take my policy parameters, and then it's going to, through the states and actions which are generated, choose an objective function that is essentially evaluating our policy. So we can think about the system or this adversary as providing feedback to the learner by picking out a loss function. And then finally, the learner is going to update the parameters based on this loss. And this process will repeat by advancing to the next round. So why does this online learning framework make sense for robotics? So there's a couple reasons for this. So one is, in addition to sort of fitting the overall structure of robotics problems, this theoretical framework actually matches the properties of data which are encountered in robotics problems better than, for example, empirical risk minimization. So just a reminder, empirical risk minimization is the dominant paradigm for thinking about machine learning algorithms. It's often used to guide how we think about basic machine learning problems like classification or regression, but it also makes a number of strong assumptions about data and models which may not hold in practice. So for example, we assume that our data is IID, that it's collected in batch, and that it's generated by a known class of models. But in robotics, none of these things are true, right? So robotics data is not independent and identically distributed. Robots collect data that evolves over time, and they interact in a closed loop with the environment, right? So like every time a robot takes an action, it changes the distribution of data, which it's receiving through its sensors. And in practice, like data is often not batch. So if I'm running a data is literally streaming through my sensors and is being collected through this interactive process. And finally, the models that we try to learn in robotics are necessarily approximate. So if we're using a model of the robot's dynamics or something like this, and the robot is operating in a fairly complex environment, that model is just not correct. It's useful, but not correct. So the data generating process typically does not live in the model classes that we're trying to fit in robotics. So this means that we need a fairly flexible class of learning algorithms that does not make strong assumptions if we want to properly learn while robots are operating in the real world. And so this is what online learning does. So unlike empirical risk minimization, it makes minimal assumptions. And it mainly focuses on this concept of regret minimization. Okay, so I'm gonna kind of take a short aside into the world of online learning. We're gonna go through a couple simple algorithms, then we're gonna come back to robotics. Let's just look at this concept of regret minimization in more detail. So here we're going to discuss two types of regret. There's kind of the standard notion of regret, which I'll talk about first, and then we'll talk about this kind of interesting notion of regret, that tracking regret, which is a little bit more complicated. For a stationary policy, so basically a policy which works well everywhere in the environment with the same parameter setting, minimizing regret means learning a sequence of policies that compares well with the best policy in my policy class in hindsight. So in other words, I want to learn rapidly. I want to do the best that I can given the policy class that I have and the data that I've seen so far. But there's also a notion of having a non-stationary policy. So maybe as I sort of traverse my environment, I want my policy to take on different parameters. So for non-stationary policies, I want to learn a policy sequence that is performing as well as possible with respect to the best sequence of policies that I could have executed if my robot was like in different states. And this is something which is much harder to minimize. We'll go through an example of this just so you can kind of see what I mean by tracking regret in a non-stationary policy. So we'll do that in a few slides. But for now, we can think about online learning as focusing on notions of regret like these. It's also very general in that it doesn't make strong assumptions like the IID assumption, and learning is agnostic with respect to ideal systems. So I'm just trying to learn the best policy in my policy class. I'm not making any strong assumptions about how my data is generated. Okay. So let's take a brief detour into the world of online learning. And for those of you who see a lot of math and their eyes start to glaze over, we will eventually get back to awesome robots, but we're gonna kind of build up this set of tools first. All right, so we're gonna look at a few well-known online learning algorithms that attempt to minimize static regret. So really the simplest algorithm is called follow the leader. And the basic idea is that if I find a set of parameters that has minimized the sum of every loss function that I have encountered so far, then this may do well on the next unseen loss function. So in other words, I'm trying to choose the best policy in hindsight. And for well-behaved loss function, follow the leader achieves on the order of logarithmic regret. In the worst case, follow the leader algorithms can severely overfit data, leading to some pretty undesirable behavior. And to contend with this problem, we'll often add a regularizer to my objective here. So if you kind of look at this equation and follow the regularized leader, this term here is a Bregman divergence, which prevents the solution or like the policy parameters, if we want to think about it this way, is changing too much in between rounds. And the choice of regularizer generally depends on the problem you're trying to solve, but common regularizers include things like quadratics, Fisher information metric, or like the KL divergence. And instead of minimizing the sum of regularized losses directly, we'll actually often reduce this problem to a simpler one. where we focus on linear loss functions. So the linear coefficients G here form an inner product with our parameters theta. And this still works for any problem of interest, as we can just choose GI to basically be the subgradient of an arbitrary loss function, Li. Okay, so we're essentially constructing this like surrogate loss. Okay, and then finally, we can simplify this even more, and this gives us mirror descent, which has strong connections to follow the regularized leader, as well as a gradient descent family of algorithms. So first, we can interpret mirror descent as basically a lazy version of follow the regularized leader. So basically, you're only minimizing a linear approximation to the loss function at this round, combined with a strongly convex regularizer. So you don't really care about the loss functions from previous rounds. It's a bit more efficient. And to just give you some sort of intuition about how it works, it basically works like gradient descent. So let's just look at this toy example. So here the goal is to find the minimizer of some convex function f. So using mirror descent with a quadratic regularizer gives us the following optimization problem at every round. And you can see eta here on the regularizer tells us how much to regularize. Now, if we take this objective, so we take the derivative and set it to 0, and then solve for x, the solution to the surrogate problem is exactly a step in online gradient descent. So we can get online gradient descent out of this as a special case. And again, note that eta plays an important role as a step size here. Now, different divergences can result in different algorithms. So mirror descent actually defines this whole family of gradient-based optimization algorithms. So for example, if I use a Fisher information metric, I get gradient descent, but I can use things like, natural gradient descent, but I can use things like the KL divergence as well. Okay. So let's now talk about some less well-known online learning algorithms. So mirror descent, what we just talked about, attempts to learn a sequence of policies that compares well with the best policy in my policy class in hindsight over multiple, and then like over multiple steps, it should be converging to this ideal policy in my policy class, which I'm sort of noting here as theta star. So it's doing something like this, where descending this objective function, trying to find the best policy in my policy class. But what if your best solution is actually changing over time? So in this case, the problem becomes much more difficult, right? Because the target that I'm trying to get to, like the best policy, is actually moving. So what you may want to do is try to track the best sequence of parameters, something like this, or sequence of decisions. And so the question is, how do you do something like this? So this is a case where we're trying to minimize what's called tracking regret. And we can do this using an algorithm called dynamic mirror descent. So in dynamic mirror descent, at every step, and we're updating a surrogate loss function, which is just like vanilla mirror descent. But then we're going to use a second predictive map to anticipate what the next parameters are going to be. So if the predictive map actually accurately captures the comparator sequence, this thing that we're trying to track, and how it's evolving, then my dynamic mirror descent should have low regret. And we can actually show that it has regret, which is parameterized by the accuracy of our predictive model. So let's just kind of see how this works. So at the current time step, we would take a step of mirror descent towards our current solution. And then next, the optimal solution moves, and we're going to anticipate the move with our predictive model. We're then going to take another step of mirror descent. The solution will move again. We'll anticipate that. We take another step of mirror descent and keep repeating this process until we converge to the changing solution. So we're essentially doing tracking to track this sequence of optimal solutions to our problem. All right. So that's our kind of quick foray into online learning, and we're going to come back and use some of these tools to do cool robotic stuff. But in general, I think about online learning as a perspective that allows us to, or a framework, right, which allows us to unify algorithms. Many algorithms kind of fall out of it as special cases. It also explains empirical performance that we see in methods like tracking and model predictive control, as well as areas like online reinforcement learning and imitation learning, and also suggests new approaches. It allows us to build new algorithms, and we'll see how that's true in the next section. Okay. So actually, before talking about online learning and model predictive control, I want to sort of come back to this abstract perspective on robotics and talk a little bit about simulation. So returning to our diagram of the learner, I want to make just a few additional observations. So first, the state or the feedback that we get from the system when we execute a policy is typically not actually state, but rather a partial observation of state. This can cause difficulties, and we should always sort of keep this in mind when we're trying to build learning systems for robots. Second, the objective function that we're trying to optimize is subjective, right? So when we're trying to get the robot to learn, we design an objective function, like we as the engineer or the designer will just pick something out and hope that it works. If it doesn't, we may then change the objective and repeat this process. But this is really important because different objective functions can have a significant effect on learning algorithms. And examples include things like reward shaping and reinforcement learning, or using imitation learning and imitating an expert rather than solving a full reinforcement learning problem. The final thing, and what I really want to focus on here, is that it can be hard to predict what will happen when I update the parameters of some policy which is running on a robot. So if my system or policy is really complicated, changing the parameters might result in unexpected behavior, which is always bad for us in robotics, right? Unexpected behavior can be very costly. You can think about like robots falling down or autonomous vehicles crashing. Every time we sort of interact with the system and change these parameters, this is also potentially a slow process. We have to kind of reset things and run the robot in real time and that sort of stuff. So ways of mitigating some of these challenges, like the cost of interacting with the world during learning, is using more interpretable policies. That's kind of a simple thing. Maybe we can better predict what will happen. Or engineering the task environment so that the robot's interactions are safe and simple and repeatable and therefore predictable. Or it's possible that we can actually predict things very well in a particular task, maybe because of some of these other things. But if we can predict things well, then we can use simulation. So if we can predict the outcome of changing policy parameters, then why not just learn in simulation? This allows us to update parameters cheaply without having to run real-world experiments, which again can be very slow and costly. And so here, this looks just like robot learning. We essentially replaced this system that you saw on this slide with the simulator here. And you can think about the simulator as basically, again, the policy, the robot, and the environment, but just in simulation. And so we can think about simulation as a cheap way of doing learning. It basically allows us to cheaply generate data which can be used to update some parameter without interacting with the real world at all. Now, of course, the whole point of training is to find parameters which actually work well on the real system. And we have to think about that. And so it's useful to think about the simulator as something which is just very different than the real system that we're working on. It's this approximation which makes things less expensive for learning algorithms, and something where we can try things in simulation without incurring the real world cost. So once we've updated our parameters in simulation, we can run these on the real system, but there's a good question, which is, will those parameters actually work? There's often a gap between what happens when you run parameters on the real robot and then in simulation, and on the real robot and in a real system. And we'll call this the reality gap. So if the simulator is not accurate in just the right way, then the robot may fail at its task in the real world. And that's something we have to really watch out for. So a potential solution to this problem is to use sort of a two-stage approach. So first we can learn in simulation and then fine-tune on the real robot. And the hope that is that simulation will provide a cheap way of getting us most of the way to something which works well on the real system. Okay. Now, an interesting thing here is that the simulator and the real system, because they're not the same thing, we can potentially be interacting with both of these things simultaneously. And that actually starts to look like model predictive control. And so the idea here is that you have a learner which is interacting simultaneously with the simulator while it's operating in the real world. And it's using its interaction with the simulator in order to make good choices for its policy parameters. So we'll talk about this in some detail. It's okay if you don't quite get the picture right here. We'll actually go through how this works in the next part of the talk. Okay, so this is really the meat of the talk today. We're going to talk about this online learning perspective on MPC. And we're going to take these ideas of simulation and online learning and show how we can combine them in order to derive model predictive control algorithms. In order to frame this, we're going to discuss a pretty cool robotic system that we worked with at Georgia Tech. So here's one of our robots. It's a high-speed off-road ground vehicle. It's built in collaboration with several labs in computing and aerospace engineering at Georgia Tech. And our goal is to race these vehicles faster than a human can pilot it in sort of less prepared terrain, so on dirt tracks and in off-road terrain. To give you a little bit of an idea of what these robots are actually like. So they're 1/5 scale trucks. They're about 1 meter long. They weigh roughly 45 or 50 pounds. They have electric motors with a top speed of 50 to 60 miles per hour. They have cameras, IMU, GPS, and wheel speed sensors all on board. And they also have significant onboard compute. So they have i7 processors and a GPU just on board the vehicle. We control the car by steering and modulating speed with throttle commands. So this is basically our action space. And we can think about this from sort of a computer science AI point of view as wanting to come up with a policy which maps sensors on board the vehicle to motor commands in order to perform well at some task. And in particular, we want to design a policy which will control this car at high speeds over rough terrain without crashing. So first, I want to just give you an illustration for why this is hard. So I'm about to show you a slow motion video of the dynamics of our car as it's taking a turn at high speeds. So it looks something like this. And you can see that it's bouncing and sliding, and it has behavior which is fairly difficult to predict and virtually impossible to simulate accurately from first principles. So we can think of trying to find a policy to control the vehicle as actually an online learning problem, where the learner is tasked with choosing a good sequence of policy parameters. But it will be evaluated by the robot and its interaction with the world. Okay, so we'll see how this works. Before delving into that, I want to talk a little bit about sort of overall robotics pipeline and model predictive control. So how might we actually design this policy, which actually goes from sensor data to motor commands? So despite what some of my machine learning or even machine learning for robotics colleagues may tell you, classical engineering is a really good starting point here. We'll start by decomposing the problem into individual unit-tested components. In our current setup, the pipeline looks something like this. So perception, we're using differential GPS and IMU for these race cars to give accurate outdoor position to within a few centimeters. We're doing state estimation where we're localizing the vehicle against a GPS survey of the environment. And then we're going to assume a system model. This is something we can actually learn from data, and I won't talk about the details of that, but we have some approximate model which allows us to predict future, the effect of future actions on the system. So the focus of what we'll be talking about is this model predictive control box here. So basically after perception and state estimation, we're then going to just think about how do I actually drive this thing and choose good steering angles and throttle commands. And we're going to do this with model predictive control. So we can view model predictive control, at least the way that I view it, is it's a really pragmatic approach to designing a policy. It doesn't even attempt to build a single complex policy which works well everywhere in the environment. Instead, what it does is it uses a very simple policy class and then re-optimizes this policy aggressively at states we encounter. And as we'll see, this is something that dynamic mirror descent can actually describe very accurately. So let's see how we can view MPC as online learning. So on the left side of the screen, we're going to have the online learning paradigm, and on the right, we're going to specify choices for our particular problem. And we'll sort of talk about how these things interact. So first, each round of online learning will correspond to a time step in the system. So the learner is going to be tasked with choosing a new policy at every single time step as the robot is operating in its environment. And then second, the policy, because we have to be updating this policy so rapidly, is going to be something which is really simple. So it's going to be just a simple open loop control distribution. You can think about this as a distribution, like a probability distribution of trajectories of actions. Note that the policy is not actually even conditioned on state, right? It's literally just a distribution of action sequences. And we can think of the statistics of the distribution as the policy parameters. So here we'll just illustrate this as like a mean trajectory. So a mean trajectory of actions. But in general, it's going to be moments of a probability distribution over action sequences. Okay. We're also going to assume this simplified biased simulator that takes the current state of the system and the control distribution as input and produces a distribution of states as output. So using a dynamics model, which we're calling F hat because it's just going to be this approximate model, we can integrate the state forward in time. And you can see this here in the animation in the lower right-hand part of the slide. So the idea here is that given a state, we can evaluate the quality of a policy at that state by estimating its expected cost in simulation. Right? So the learner's updating the policy parameters. So it's handing this action sequence to the simulator. The simulator is taking a state as input, some state from the world. This is going to place my action sequence somewhere in the simulator. And then using this model F hat, it's going to be generating these states and actions. And it'll be generating a distribution of them. And that's what you can see in the illustration. Okay. Now, let's look at the objective function, which is just going to be the expected cost in simulation. So this is the expected cost under the simulated state action distribution starting at this current state ST. So now we can think about the world, like the system. It's picking out where the robot is going to be placed in a simulator because it's telling us what state a robot's in. And then the simulator generates the states and actions, and we evaluate that on our objective. So basically, by generating a state, the system is selecting a loss function for our policy at this current time step. Okay, so from the online learning perspective, our objective is to update the parameters of our policy based on the loss. And the goal is to minimize tracking regret. So one way to think about this is the objective is really about consistency in simulation. We want to update the parameters to perform well in simulation at the next time step. So in other words, we want to update the parameters so that the policy will have low cost in simulation wherever the system decides to evaluate me next. And so we're thinking about kind of the world as this adversary who is going to be evaluating our learner by choosing where in simulation to drop us. Okay. So in order to achieve low tracking regret, we're going to use this dynamic mirror descent algorithm, which we discussed earlier. And remember, it has these two steps. So in the first step, it performs mirror descent to update the control distribution so that it has lower loss on our objective, so that it performs better in simulation at our current state. And in order to do this, it's going to build a convex global upper bound approximation of the objective using this gradient G, step size lambda, and a Bregman divergence, which could be like a squared distance or a KL divergence, and then minimize the surrogate function. The gradient basically tells us what direction to take our improved, in order to improve our parameters. So in this case, in order to improve our action sequence. And the Bregman divergence keeps me close to my previous solution. So the result is an updated control distribution that performs better in the simulator for the current state ST. We then execute the first action from the updated control distribution on the actual system. And then we get to the second part of mirror descent, which is the dynamic part. Here we're going to use a predictive model to shift the distribution forward from time step t to time step t+1. And this is kind of like a state space model and a Kalman filter. So the online learning algorithm then moves to the next round, which uses the newly proposed open loop control distribution together with the next state. And the process repeats. So in summary, this dynamic mirror descent approach views model predictive control from the perspective of online learning. It applies a dynamic mirror descent algorithm to rapidly adapt a simple policy as we traverse our state space. And intuitively, if our simulator is accurate and we can predict the next state, then we should achieve low regret, according to dynamic mirror descent. Okay, now the interesting thing is this online learning framework is very general and actually provides a clean derivation of a wide range of different types of model predictive control algorithms. And there are special cases which include algorithms that we've all heard of, right? Like linear quadratic regulators, cross entropy method for MPC, and model predictive path integral control. And in each one of these cases, we can get the different algorithm by choosing different policies, picking a particular objective, and then optimizing with dynamic mirror descent. You can also get a number of new algorithms by just choosing different or having different choices for each one of these things. So I can choose different policies or different divergences, and I can end up with things like a natural gradient descent version of model predictive control. I can get bang-bang control by using, for example, a categorical distribution, a KL divergence. I can generate exponential family control. So I can do all sorts of new things by just kind of varying these parameters, and new model predictive control algorithms just fall out. Another thing which is kind of cool is that if you look at the details, this perspective suggests that many off-the-shelf MPC algorithms are actually suboptimal from an optimization viewpoint and make a number of heuristic choices which are not particularly justified. A really good example of this is step size. So step size is something which is super important in optimization, but something which is actually hidden within these model predictive control algorithms. It's a really important component for getting MPC to work well on real systems. This perspective is also just, as I mentioned before, prescriptive, right? It allows us to develop new MPC algorithms easily for a particular application. All right, so for our racing task, which I motivated this with, we're going to use variations of model predictive path integral control. So our policy is just going to be a Gaussian distribution of actions. We're going to use the so-called exponential utility for our loss, a KL divergence, and I'll show you what happens when you vary the step size, but we'll start with step size 1. So here you can see model predictive path integral control, which again is an instance of our approach. So we can compute the expected cost at each state through sampling. This is actually GPU accelerated, and we can use mirror descent to update our open loop control distribution. So on the lower left, you can see the the predictions of where the car will end up in simulation, and then you can see the car racing. And the cool thing about this is we're able to actually get these cars to drive faster than any of our grad students can pilot them around this track. It's about 10% faster, which means that it's about a second shorter lap time. This is also a very robust approach to controlling vehicles. So this is true of MPC in general. It's robust to perturbations. And this is due to the use of a simulator at runtime to understand local cost information and do fast re-estimation of the robot's state. So what we're seeing here basically is, oops. All right. What we're seeing here is the robot kind of coming around this turn fast, and there's a rock which knocks the back of the robot out of alignment, but it's able to rapidly recover. So again, on this slide and the previous one, we're using these MPC algorithms with dynamic mirror descent with step size of 1. But once we start kind of playing with the step size, we can actually get really impressive behavior using very, very little compute. So on these previous examples, we were using almost 2,000 trajectories during our rollouts when we're trying to evaluate what will happen, the distribution over what will happen in the future. But by adjusting the step size, we can actually get robots to race almost as fast and around fairly complex tracks like this one with only 64 trajectories. And this can really help us when we have limited onboard compute or when we're doing, when we're trying to control higher degree of freedom robots. So we've also applied these algorithms to robotic arms and things like this. Okay, I want to show you another more recent example and a little bit of the work that we've been doing here at University of Washington. So we have a large ClearPath Warthog robot here at UW. This is actually, it's about a 5 foot by 5 foot square skid steer robot. It has similar onboard compute as our high-speed auto rally platform. We're using LiDAR and a camera for perception. It also has RealSense and GPS, but we're not actually using that. And our goal is to drive this robot robustly through complex terrain. And I just sort of want to show you how this MPC algorithm that I've been talking about works inside a sort of larger, more complete system. So here you can see what our overall stack is doing. We're basically fusing semantic segmentation of camera images. This is in the upper left. And LiDAR segmentation. There's a fused image in the upper right of LiDAR and the camera segmentation. Green corresponds to easy to traverse terrain. Yellow is easy off-road terrain. Orange is difficult, and red is considered to be like a lethal obstacle. Now I could give you a whole talk about the perception system, which is super cool. We'll leave that for another time. But I just want to show you that like MPC is also running on this robot, and it's able to get it to robustly pilot the robot through various types of terrain. So on the lower right, you can see a map which is being built on the fly. And again, we're using the same MPC algorithm to control the robot. So if you look really closely in the lower right, you can see just an overhead view of the robot, and there's a line kind of coming out the front of it. That is the prediction from our MPC algorithm, which is being rapidly updated using dynamic mirror descent MPC. So this is the system. And here you can see it just running on a dirt path. And basically, it's now in the context of this entire perception stack where we're evaluating all of the terrain around the robot and generating maps online. And then down below, you can see the MPC algorithm basically predicting where the robot is going to end up as it tries to get to some goal. There's also a plan which is not being illustrated here that it's trying to follow in order to get to the goal region. Now, the cool thing about this system is that this MPC algorithm allows our robot to be extremely robust to different conditions. So with no changes whatsoever to the underlying MPC algorithm, or even the models that it's using, we see that a robot can actually traverse totally different environments with significantly different dynamics. So here there's lots of slip and compliance as the robot is driving through the snow. So I'll let this play for a little bit because there's kind of more interesting terrain coming up. But the idea is that this sort of aggressively optimized approach to adapting a very simple policy, which is being used on the as the sort of mid to lower level controller on this robot, allows us to effectively deal with like this deep snow and slush. Here it's about to stop as it's reached a goal location, and then it'll start up again and sort of plow through the slush to continue on its journey. So we can get this robot to drive through like pretty ridiculous conditions using MPC. Okay, so I just want to finally very briefly talk about a few ways of extending the paradigm that we've discussed today. And we're going to do this by kind of going back and now thinking about this overall view of model predictive control, like this perspective on it. We've seen how this is related to online learning, and we've seen how it can be an effective approach to controlling high-speed and off-road vehicles. But this MPC algorithm, well, adaptive, right? Like it's adapting to the different states that the robot finds itself in, is not itself learning to improve from experience. So ideally, we would like the MPC algorithm to get better at adapting as the robot interacts with the environment. Now, one thing we can do is add feedback into the system sort of this way. And so this is where like these diagrams really help me kind of think about how the connections between these algorithms. So in the lower part of the system, if you just look at like the learner proposing a parameter for my policy to the system generating new states and actions, that interacting with my objective function, and then the learner updating, that part of the system is basically just an RL algorithm. And so one way to improve model predictive control is by integrating reinforcement learning with model predictive control. And one way that we've started to do this is by learning an additional Q function from the data collected during execution. So what this allows us to do is use our current model predictive control algorithms as a baseline, which we already know work pretty well. But as we interact with our environment, we're collecting lots of data about the robot's interaction environment, the states and actions that it's encountering. And that data can be used along with fitted Q learning to learn a Q function from the real world data. That Q function can be blended together with model predictive control in its cost function and used in simulation in order to choose better actions. So I won't go into details of that, but that's the subject of a recent paper that we have called MPQ Lambda, which blends a learned Q function that we learned during a robot's operation with Monte Carlo rollouts in simulation. And this is very similar to forward-looking temporal difference learning, just in this kind of model predictive control context. So this is an upcoming paper at iClear. Another thing I just want to very briefly mention is we're also doing some work on legged robots now. So we have a few of these Unitree A1 robots and a Boston Dynamics Spot robot. But for the A1 robots, one goal that we have is trying to get the robot to run efficiently, eventually over a variety of terrain. And to try to solve this problem, for a machine learning person, we could do something like just try to learn a policy that directly maps states to motor torques, which looks something like this. It turns out this doesn't work super well. So what you can see here is a solution learned in simulation. First of all, the solution just doesn't look right. It's not actually the most efficient solution, even in simulation. And there's no way that this is going to transfer from the simulator to the real robot. So we want to do something else. And just to kind of give you a brief sketch of the way that we've been thinking about this, we've been thinking about it as kind of a hierarchical problem. And so instead of just learning a neural network policy, we incorporate hierarchical structure, but we do it in a very particular way, which allows us to combine model predictive control with reinforcement learning in this particularly interesting way. So basically what's happening here is we have a high-level reinforcement learning algorithm that is learning a policy, and the action space of the policy is actually objective functions for model predictive control. So it's at every time step, the policy is picking out an objective, and then a low-level model predictive control algorithm is optimizing this objective. So this is a submitted paper, and I won't go into details, but what I can show you is that we're able to use this to learn how to get a robot to run efficiently. And one thing which is kind of cool is this robot is actually changing gaits as it's hitting different target speeds and running through this building, which is pretty nice. All right. So just to summarize, I want to leave you with a few recent papers on online learning, mirror descent, and model predictive control from our lab. We're increasingly these days focused on thinking about how to integrate model predictive control, which you already know work well on real robots, with reinforcement learning in such a way that robots are only improving with experience. And some of our recent papers, like the blending MPC and value function approximation paper from iClear, are showing precisely how to do this. So just to summarize, online learning is a perspective that can serve as a unifying framework. The nice thing about it is it provides simple derivations of fairly complicated model predictive control algorithms. It allows us to leverage insights from optimization and suggests how to build new and better algorithms. Model predictive control in general is a really effective approach to handling challenges like complex and dynamic environments with very simple models. And our takeaway is that just local fast optimization of simple policies is very, very effective in practice, and something we'll be continuing to do on our robotic systems. Reinforcement learning is a really promising area of machine learning. It can learn very complex policies and solve extremely difficult problems. It's state of the art in a wide range of fields in computer science, including solving games, dealing with perception and natural language processing. So it's truly revolutionizing how we attack fundamental problems, but how to generate and leverage data and how to actually use it effectively in robotic systems is quite difficult. So again, I think a lot of people are making progress in this area. The way that we're thinking about it is we're first framing MPC from this very general perspective, which I presented today, and then thinking about how to combine reinforcement learning with MPC in just the right way so that robots can kind of continue to improve with experience. All right, I just want to thank the grad students who've been working on a lot of the work that you saw here today. Sort of a wide range of students with different backgrounds and at different universities who have been doing the bulk of this work. So thanks to them. And then thank you all for listening today. And at this point, I'm happy to answer any questions that anyone has. Thanks.
Thank you, Byron, for an exciting talk. In the next part of this session, I will introduce Rahul Ramesh and Oleg Rubkin, who are graduate students in GRASP. Why don't actually I have them introduce themselves?
Should I continue to share my screen, or should I stop sharing?
Maybe yeah, it might work better if you stop sharing your screen.
Great.
Yeah, sure. So maybe I can go ahead first. Yeah. So I'm a second-year PhD student in CIS, and I broadly work in areas in multitask learning and few short learning.
Okay.
Yeah. Okay. Hi. I'm Oleg. I'm a fourth-year PhD student, and I work on. I'm generally interested in autonomous intelligence machines, but specifically data-driven approaches. And I work on things like model-based RL, self-supervised RL, and probabilistic predictive models.
Very cool.
Okay, so thank you for the introduction. And so we've collected a few questions for you. from the broader grasp audience prior to the talk, some of them during the talk. I would encourage the audience to put questions in the Q&A box here if you have, and we will ask them one by one. So I will let Oleg and Rahul work around with the questions, and I will butt in if I have comments to make.
Okay, so I guess we can start. So there's a question on online learning, sort of this is a more general, maybe a more broad question, which is kind of, which parts of the online learning framework are actually important? It is interesting to think about controls optimizing a sequence of policies as you presented, but it seems that the presented approaches just really maximize the cost at every time step. Yeah, that's what I also noticed. So basically the question is, does it matter whether the data are IID or not? Because if you only consider one data point at any particular time, the kind of the online learning part of the problem seems a bit lost.
So the way, so I'm not sure I entirely understood the question. So please, you know, let me know if I'm not answering it properly. So the way that the online learning algorithm is kind of set up in this case, you're thinking about the environment, right? Like the system that you're like interacting with as choosing a different loss function at each time step. Now, the way that it chooses the loss function, it can differ for different types of robotics problems. So in this case, what it's doing is it's receiving state information about where I think I am in the environment, and that induces a sort of particular loss function. Now, there's no assumption about IID, and there's no assumption about structure. So for example, you could imagine like the more error that I have in my models, right, the less I'm able to sort of predict where, like what loss function the environment will pick. And kind of the more I can think about the environment as like an adversary, right? So essentially, like in this online learning approach, I'm proposing my action sequence, and then the world is saying, okay, like I see your action sequence, and I'm going to put it right here in the simulator. Like now let's see like how good your loss is, right? So if none of your models are any good, essentially the world could kind of put you anywhere, right? Like you have no idea how to sort of optimize in order to perform well with respect to wherever the environment can put you. But there is actually some structure, and the environment is not quite as adversarial as it may seem. And so generally, this is sort of the dynamic part of dynamic mirror descent. You can kind of predict where the environment is going to put you next, and actually achieve like very low regret. So I'm not sure that entirely answered the question, but I'm happy to wrestle with it more.
Yeah, actually, yeah. So okay, that does make sense for the MPC case, yeah, because so the dynamic part of the mirror descent kind of helps you solve the online learning problem, but because you can propagate the solution from the past problem. Then I guess the kind of the similar follow-up question would be, it seems to be a very strong assumption that you just have access to this ground truth operator that just perfectly propagates the solution from the past problem.
So you don't, right? So you don't have access to that ground truth operator. So now if you had access to the ground truth operator, then mirror descent should be like converging to, you know, kind of precisely the right action that you should take at each time step. But you don't have that. And so what that means is there's going to be like error in this operator. And the amount of error in the operator is going to court, like there's a term for like regrets in the dynamic mirror descent bound, basically, which says that, you know, that regret is a function of like the error in whatever that operator is. So you'll have like very low regret if you know the ground truth like dynamics, right? And precisely kind of where you're going to end up next. But you will have regret, which is getting larger as your models become like less accurate, basically, which makes a lot of sense, right? That's actually sort of what you want to see. You want to say like, okay, I have an approximate model. It tells me something which is better than nothing, but like I'm going to expect to like large regret if I'm using that. If I had the perfect model, I know precisely how my robot interacts with the system. I'm going to sort of be able to choose precisely the right action. You know, I'm going to like quickly converge to like this right action sequence, and I'm going to be able to do super well on my particular task. So some of these like ground vehicles, they're somewhere in between, and you know, the slop due to snow or slip on like on granular media or things like that. The slipperier the environment is, the harder it is for me to predict what's happening, kind of the more regret I'm going to have, and the less well I'm going to be able to control this thing. And that just makes sense.
But if I can chime in, isn't the shift forward operator also a function of the data distribution or how it evolves down the future? That you have really no bets on, right?
So the shift forward operator is something very interesting here. It seems like a very simple operator. All I'm doing is basically I have an action sequence and I'm just saying, well, I executed this first action, so just kind of shift forward in the action sequence, right? Like take action 2, 3, 4, 5 as like my next actions. So this seems like a very, very naive operator. But it's actually not, because the action sequence itself has been shaped through like these multiple sort of previous time steps of optimizing it based on, for example, the dynamics in your simulator, right? When you're actually sort of like rolling out your trajectory, you're generating a state sequence using this dynamics model, and that's generating your cost, which is being used to update your action sequence. So the updates to your action, like these gradient updates to your action sequence, are actually a function of like your dynamics model. The better your dynamics model is, the better you're able to predict how the sequence of actions will result in high or low cost. And then that kind of tells you how to update it. And sort of all of that information is sort of in the shift operator in some sense. When you do the shift, you're saying, well, I expect my next sequence of actions to be the correct ones, but you expect them to be the correct ones because they've been updated multiple times through gradient descent based on whatever your dynamics model is. So if your dynamics model is bad, the shift operator will be bad. If your dynamics model is really good, the shift operator will actually be good. And that's kind of how it comes into play. So it's a bit subtle, but kind of interesting.
Yeah, so I was wondering how you would make a distinction between online learning and adaptation. So for the case of adaptation, you have like say where the task changes rather drastically from say walking to running, and I was wondering if online learning is still applicable in such a scenario.
So, I mean, online learning is just a very general framework. It's a way, like my view on it is it's a particular way to think about learning, and specifically to think about theory, like what your learning algorithm is doing and what assumptions you're making. And it admits certain solutions. So you can say, if the assumptions that are being made in online learning are met, then the solutions that I get from these like optimization algorithms are going to behave as expected, right? So so I guess I think of online learning this way: a framework for a good theoretical understanding of what your algorithm should do, and a way to use optimization techniques from people who spend a lot of time trying to figure out how do you optimize online learning algorithms effectively, or online learning problems effectively, how to use those maybe in robotics. So in terms of like specific problems and adaptation, the question is, can you take a particular robotics problem and frame it as an online learning problem? If so, you get the theory and the algorithms sort of for free, and you can assume that they're going to work well because the theory will match the assumptions. So examples of this, like, I talked about model predictive control today, but you can also look at like filtering. So for example, Kalman filtering or Bayes filtering, these are special cases of online learning as well. As you can imagine, you're trying to update some state or some prediction about the future conditioned on some sequence of observations. And you can view this through the lens of online learning. Now, that also means you can develop like new filtering algorithms, which are based on, let's say, like mirror descent, as opposed to, let's say, just something like natural gradient descent, which can generate like Bayes filters and stuff like this. So so I've punted a little bit on this answer. I've basically said that, it's just a theoretical framework for kind of like understanding algorithms. And if you can frame your algorithm that way, then great. And I guess I think a lot of adaptive problems that we care about in robotics, everything from like filtering to control, can be understood this way. And we can use pretty powerful optimization tools then to help us to solve those problems more effectively. So that's kind of how I view it.
Actually, if I may ask a follow-up question about it, I find it very confusing that online learning, the way I personally would think of online learning is I adapt my model and then I get more data from a slightly different distribution at time t+1. But in your case, it's really online optimization. You never actually exploit or the system never sees more data at time t+1 because the next time step occurs after that, immediately after your model adapts. So what is the difference between online optimization, which is what filtering, Bayes filter, MPC would fall into, and online learning? What are we learning here?
So the way that you can maybe view, so let me try to like sort of step back, and then feel free to interrupt me if something's not making sense or I'm not being clear about something. So the way that I kind of think about online learning is, all right, I have a parameter that I'm updating. It could be like the parameter of a model, or it could be like a decision that I'm making. And I make that decision. So I make the decision, then someone gives me a loss function, right? And says, like you made the decision, now I'm going to evaluate it, and you're going to now suffer some loss, right? And when you suffer that loss, you now want to update your algorithm so that you're going to make a better, try to make a better decision at the next time step, so that even if like the world is kind of choosing bad loss functions for you, you're still going to try to do well, right? So this is kind of how I think about it. It's like a sequence of decisions, which are then evaluated by, you make the decision, someone gives you a loss function, you make a new decision, someone gives you a loss function, you make a new decision, someone gives you a loss function. So it's that process. And the goal is to achieve low regret on that sequence, right?
Okay.
Are we okay so far? So for like filtering, you want to be thinking about, so it depends on precisely the decision you're making, but like so you can basically write a Kalman filter as looking something like this, where your loss functions are restricted to be like squared losses. And essentially what you're doing is you're trying to update a parameter, which is going to be your like state, so that you achieve low loss at each round. For controls, like for here, what we're doing is we're updating our policy parameters so that we'll try to achieve low loss in simulation at the next round. Now, in like in this dynamic case, so in sort of the standard mirror descent case, you could imagine something like at a particular time step, you generate like an action sequence, and then you receive a loss function for that action sequence, right? And so you're like at a particular point, let's say, right? And then I receive like a loss function for my action sequence. I want to update my action sequence. And then someone can choose a loss function again, and then I update my action sequence and choose a loss function again and update my action sequence. So if my state stays the same, I'm sort of in this local region, and I can kind of continually use mirror descent to get better and better and better solutions at this state, which is fine. And in fact, even in the algorithm I presented today, you can do that. You can take like 10 steps of mirror descent at one time step in order to sort of adapt your, right? So I can take as many of those steps as I want. But then at some point when I advance the time step, the world is going to come back and it's going to put me somewhere else in simulation. And this is where the sort of the shift operator comes in. If my shift operator is good, I will be able to anticipate where it's going to put me. And I'm going to be able to kind of continue to get a better sequence of actions, right? If my shift operator is bad, then I don't know where it's going to put me. And I have to be very careful, because if I optimize my action sequence to be really good at this state, and then the world puts me somewhere else, and my shift operator doesn't, you know, like I think, oh, I'm going to move, you know, I'm going to take this action, I'm going to move sort of, you know, just a small amount forward, like my vehicle is going to move forward. But if someone picked up my vehicle and threw it across like the track, and I'm now suddenly in like a totally different state, like my dynamics model didn't account for that. And if I over optimize at my current position, I'm going to do really poorly on like the next round, right?
Okay. Yeah.
So, so that's where, like, if the dynamics model can anticipate things, I can sort of across rounds optimize my action sequence so that it's going to work really well. So typically what would happen is I start out and I say, I have, let's say, like a straight action sequence I'm on the track, and I start to drive. And like at each time step, I do like a gradient update essentially to my action sequence. And it got a little bit better. And then I shift, so I predict where I'm going to be next. And then at the next time step, my action sequence is already actually pretty good. So I'm going to make it a little bit better. And then I can repeat that process. If I have a lot of compute, I can do many rounds of MPC, but of mirror descent in between the dynamic part.
Time step. Yeah.
Yeah, but you also have to be careful. Like this is where sort of the Bregman divergence comes in, and like some regularization parameter, because you don't want to sort of overfit to where you are. If you're going to be put somewhere else and you can't entirely anticipate where the vehicle is going to be next, then you can certainly like overfit and have a really bad solution at the next time step. So for example, if my vehicle hits a rock and is now like oriented slightly differently, now, and I thought I should be going straight. And so I have this like straight action sequence, and now I'm like oriented slightly to the side. And now it's going straight off the track, right? Like now I have really high loss. And so the dynamic mirror descent algorithm is going to be sort of trying to trade these things off against each other and end up with something which is robust to possible perturbations. So there'll be a distribution of trajectories, and sort of like the wideness or narrowness of that distribution will have to do with sort of how robust I'm trying to be to perturbations and how good or bad my model is.
Okay. Thank you. That is very illuminating. I want to change gears a little bit and talk about RL. And I see Rahul has put in a question.
Yeah, so one of the takeaways from your talk is that like a simple MPC controller is very effective. So can you use like a raw sequence of observations to improve this controller? So maybe borrow methods from, say, imitation learning from RL or something of that sort.
So there's a bunch of really interesting ways of improving this controller. Here are a few. So one thing you can do is try to improve, this is like sort of the most obvious thing. You can try to improve the dynamics model. So, you can say, I have a simulator and I want to make this simulator better. So I generally think of models as just simple simulators. So you could start with like a very simple, I've got like a unicycle model of my skid steer Warthog. And it's super simple. It doesn't capture, very much, but it might be enough for MPC to work effectively. So I start with that. And I could try to set the parameters of that model. I could try to augment it with a neural net so that it becomes more predictive. Anything which is more predictive would help me with MPC. So that's a simple way of trying to improve the MPC algorithm, get a more predictive model. But there's more interesting and maybe better ways of improving MPC algorithms. So one is by changing the cost function that you're using. So I can have a very simple model, and I have this cost function which like I specify, but maybe what I can also do, so consider the following problem, I guess, with MPC. So MPC, I'm doing some rollout, right? And it's like a receding horizon algorithm. So I do some rollout and I'm looking, you know, for a vehicle, let's say 50 meters in front of me. If I'm looking at that 50 meters in front of me, I'm evaluating each one of these trajectories based on just that horizon. There's going to be some terminal cost associated with each one of these trajectories. What should that terminal cost be? So an obvious choice for the terminal cost is something like a value function or a Q function, something which tells you about, you know, the future expected cost after the end of that rollout, right? So without that, without like a good sort of notion of value or something close to a value function for the terminal cost, these receding horizon methods are literally going to be myopic, like they're going to be short-sighted. And sort of obvious thing is if you don't know what a good terminal cost function is, it's something that you could learn. Like you could learn a value function or a Q function that you can kind of plug in at the end of your trajectory. Now there's several papers which have done stuff like this, right? If you have a good value function, this leads to what's called like infinite horizon MPC. So you have the rollout, but then the value function is taking care of like the rest of the horizon, like to infinity. And so it's a way of augmenting your MPC algorithm. People also use planning, right? Like you can say, I'm using MPC in conjunction with a planner, and I kind of like am hooking into the planner, or I'm getting some cost which is relative to some plan. And that in some sense is telling me about kind of like the long range cost or value of any particular action which I choose now. But here's my point. Like if you think about having a terminal value function or Q function, that's something you can learn, and something you can learn from like real data that you're collecting as your system moves through an environment or works on a robotics task. So this is a different way of improving MPC through learning by basically augmenting the cost function with cost which is related to sort of real world cost that the robot is experiencing. So now here's another thing you can do. If I have like I'm looking, let's say 50 meters ahead in my robot, or I'm predicting, you know, a few centimeters ahead for like a reaching task or something like that. And then I have some terminal, let's say Q function that I would get from like RL. As that Q function gets better and better, so the more I interact with the system, maybe my rollouts for MPC or the horizon for MPC should get shorter and shorter, right? If my Q function was perfect, I wouldn't even need to do rollouts. I just query the Q function. You can still view this, by the way, as like online learning, where at every instant, your cost is the Q function and you're not doing a long rollout. So one thing you can do is as your Q function gets better and better, you can shorten the length of the rollouts for MPC. Another thing you can do is you can have variable length rollouts for MPC. So in some areas of the state space, maybe you're relying more on your simulator and less on a cost function or a Q function, which is inaccurate. And in other areas, maybe you rely less on the inaccurate simulator and more on a Q function, which is very accurately estimated. So that there's kind of like a whole other dimension that you can look at there, and you can improve MPC by sort of lengthening or shortening the horizon. Another thing you can do is you can use the Q function at like every point along a horizon, and you can sort of blend that with cost. And that's something that we were doing in our sort of current iClear paper. Long story short, there's multiple different ways that you can sort of improve the effectiveness of MPC by leveraging tools from machine learning or reinforcement learning, by learning better models, by learning, more effective cost functions, by building more complex policies, or by embedding MPC within RL frameworks. So I think there's just a ton of open stuff that people could be looking at if you want to sort of start from an MPC baseline that we already know works well and just try to improve it as we collect more data. And I think this is a really promising area of research, but there's like a dozen different ways I could just rattle off on how to potentially do that.
Have you tried to use RL for rally racing directly? And just as an academic exercise of whether you can do it? By that, I mean model-free RL, let's say.
Yeah, so we've used imitation learning, not model-free RL. So what we've done is we've basically had a deep neural network which maps images and wheel speeds to steering angle and throttle, and then learned that neural network via imitation. But this is not the best way to do it. And even in that case, we basically were using the MPC algorithm to train the neural net. So the interesting thing about that is you can get a neural net which maps images to, so it's essentially learning to see. But the algorithm, the expert that it's imitating is a MPC algorithm which is using GPS and stuff. And so one way to look at sort of what we were trying to do there is distill an MPC algorithm to a deep neural network, but also allow the network to use a different, cheaper source of information to drive the car. Just using RL is going to be a total disaster. And the reason is because it's not easy to accurately simulate these vehicles at all. So just trying to train it in simulation is really hard. It's not going to result in a policy which works. And the second problem is actually doing RL in the real world on the cars is a horrible idea because the cars crash. And you can look at this as reset is really expensive for the RL system. So I can run it, I can do some exploration, I can explore some new states, crash the car, and then it takes us a month to reset the system so I can collect more data, right? So this is not, and it costs a lot of money. So this is not a great strategy. I think one of the things that we're really sort of experimenting with the legged locomotion is saying look, we want real robots to actually be using RL, but where should RL be in this stack? What sorts of things should RL be doing? In my view, it should not be mapping, states to motor torques. That doesn't make any sense. RL can be used at a different level, a different level of abstraction. For any of these policies, the policy can make any decision it wants. It can be the parameters of another policy, right? It can be choosing cost functions, like what I just briefly mentioned for the legged locomotion stuff. So RL can sort of be operating at different levels of abstraction, which I think are sort of much more effective for real systems. So you should think carefully about the problem, where can I use RL? How can it make sort of non-trivial decisions, but how can it do it in such a way that whatever decisions it make doesn't break my system?
Break things, yeah. Thank you. That's a very good end to a talk on learning and robotics. Thank you for answering the questions. Very happy to have Grasp listen to them. Attendees, if you have more questions, you can go to Gather Town, and where Byron might be available for some time, and we'll end the panel here.
All right, thanks a lot for having me.
Thank you.
Thank you so much for everyone to join us today. Please tune in next Friday, April 16th, for the next Grasp on Robotics speaker, Dr. Drew Bagnall from Aurora. For more information on these and upcoming events, please follow us on social media or check out our website. Thank you again. Have a wonderful weekend.